Hi students, welcome to a video on Opamp circuits. So in this video we will see practically how does an inverting amplifier experiment can be conducted. The objectives of this particular experiment is to understand the amplification of AC signal or the DC signal by the operational amplifier, which is Opamp. In this case we are considering mu A741 as the Opamp, and we will also see the frequency response of this inverting amplifier, and we will also try to understand the limitations of this inverting amplifier circuit. So as it is mentioned there, so we have 741, so which is a 8-pin DIP package. So when I say DIP, it is dual in package. So on either side we have 4 pins. So the numbering goes this way. This is 1 2 3 4 5 6 7 8. So the pin numbers and their function is listed here. So this is the inverting terminal, pin number 2. Pin number 3 is the non-inverting terminal. Pin number 4 is minus VCC. Pin number 6 is output. Pin number 7 is plus VCC. So actually this 741 operates with dual power supply. So it requires both plus VCC as well as minus VCC. So this is a circuit diagram what we have for the inverting amplifier. So as you can see, so the pin numbers of all these pins have been written. So pin number 6 is output, 7 is plus VC, 4 is minus VC, 2 is inverting terminal, 3 is the non-inverting terminal. This is a circuit diagram of the inverting amplifier. The expression for the gain will be minus RF by R1. So here we typically use a decayed resistance box to change the gain of the amplifier. So we keep it R1 a constant value. So this is actual circuit diagram. The implementation of the same circuit using analog discovery kit, we are going to connect the input through a wavegen 1. We want to see the input also, so that is seen using C1 plus, that is channel 1 of the scope, and we are observing the output in second channel, that's why it is C2 plus. This is grounded, we'll be connecting plus VCC minus VCC. So I have the connection made here, so we just have to look at the connections. So these are the connections that are made. Of course we are connected with Opamp, and all those things are done on the breadboard. So let us begin our analysis. So before we start anything, so this is because this has this uses dual power supply, which is plus VCC minus VCC. Now output will be swinging around 0. So it will going to have, of course, the output of the op-amp is always a pure AC signal. There will be no DC shift in the waveform. So in an ideal case, so that's why it will be around 0. It can go up to ideally plus VCC and minus VCC. So this is the available ideal swing that we have. Since this operational amplifier has so many number of transistors inside, so in order to keep them in the proper operating conditions, we need to dedicate some voltage for the transistors to operate satisfactorily, so that the output voltage will not go up to plus VCC, rather it will be going up to only plus VSAT. So typically the swing will be from plus VSAT to minus VSAT. So first and foremost thing what we have to do when we are conducting the experiment is we need to find what is plus VSAT and minus VSAT. So output voltage will not go beyond this plus VSAT, and the output will not go below this minus VSAT. So that's why knowing this plus VCC plus VSAT and minus VSAT is very important. So plus VCC minus VCC is the voltage that we are supplying from our analog discovery or from any power supply, that you will be knowing. But from op-amp to op-amp, this plus VSAT minus VSAT will be keep changing. So this is the expression of the operational amplifier, because it's a differential amplifier. So under open loop condition, so what do you mean by open loop condition is, here you can see this is RF, which is actually giving the feedback from output to input. when I open this, when I just take out this RF, it becomes open loop. So under such condition, the output voltage is A0 multiplied by difference of the voltage at the non-inverting terminal minus voltage at the inverting terminal. So this is the expression for the output voltage of an op-amp under open loop condition. But for this closed loop circuit, so we call this as an inverting amplifier. The gain expression is minus RF by R1. So in order to find plus Vsat minus Vsat, so I need to have a very large gain, so that because it should reach the saturation. So let us open this RF and try to find out, or you keep this value of RF very large and apply 1 volt. So the purpose of keeping this open or making it very high is to ensure that output goes up to plus Vsat and output go down up to minus Vsat. So for that purpose, so I will either open RF or keep the value of RF in terms of hundreds of K or tens of K and apply input voltage of 1 volt. So I'll do the same thing here. So let me have the value of RF as around, okay, I just kept the value of RF as 100K. So before that, let me just turn on this analog discovery. So now I have turned on analog discovery. So let me give the supply voltage. Supply by default it will be 1 and minus 1. So I'm making 1 and minus 5. So now I'm applying this. Okay, I'll apply both of them. So both of them are now applied. Excuse me. So let me apply a sine wave of amplitude 1 volt. Let me keep the frequency around 100 hertz. Let a bit low frequency. So now before I run, let me take the scope also. I'll take the scope. So this is my scope. So let me change this time base to around 5 milliseconds so that I can see around okay 5 to 10 cycles of the waveform. I will run this wavegen and I'm just running this. You can see now I'm getting, okay, let me see the input also. Input has got opened. Okay, this is my input channel 1, and let me adjust this time range to appropriately this value. Fine. So now if I just go back to this and try to see what's happening, actually what is happening now is I'm applying. So let me just go back to the circuit and try to understand what's happening now. So here this is minus, plus this I have grounded, and I made this very large value, and this is now, or you can just open it, it doesn't matter. So it is now R1 RF. So this is my Vin that I applied. So assume that I'll just open. Okay, let me just open that also. So I am just opening. So when I opened it, the circuit is only this. So this is minus, plus I'm grounding this. I'm applying the input to this negative terminal. This is my V0. Of course, I have plus VC minus VC. Sorry, plus VC minus VC applied. So what is V0 expected? V0 expected is A0 times voltage at the non-inverting terminal minus voltage at the inverting terminal, that is Vf minus. So what is voltage at the non-inverting terminal? That is V plus is actually grounded. Can you see here? This is actually grounded. So what I have is V0 is equal to A0 0 minus Vin. So you're comparing, or your output voltage is A0 times minus Vn. So what is Vn now? So Vn is a sine wave. So let me consider this is my time. Let me consider this as my input voltage, which is a sine wave, So this is an amplitude of 1 volt. This is minus 1 volt. This is 0. And let us assume A0 is equal to some 1000. A0 is equal to some 1000. The value of A0 is around 1000. When it is 1000, we know that it is 1000 into 0 minus Vin. So you have Vin. So when Vin is greater than 0, when it is greater than 0, So what we are expecting, A naught is equal to 1000 times V in. Okay, let me just take V in is equal to some 1 volt. So are you expecting this as -1? So are you expecting it as minus 1000 volt? When V in is less than 0, so let V in be equal to -1. When V in is equal to -1, so what is A naught as per this equation? Sorry, not A naught, this is V naught. This is, sorry, this is V naught. So let me take A naught is equal to 1000. This is the open loop gain, which is very large. So V naught is equal to A naught times voltage at the non-inverting terminal, which is 0, minus voltage at the inverting terminal, which is the input voltage here, which is the input voltage. So now when input is greater than 0, that is during the positive half cycle, output has to be minus 1000 volts. When the input is negative, when the input is below 0, so as per this equation, it is 1000, 0 minus of -1, which has to be 1000 volts. So is it possible to get minus 1000 volt and plus 1000 volts? It's highly impossible. So let us see what we are going to get. So we will see when the input is positive, you will be getting an output voltage which is somewhere here like this. So when the input is negative, the output voltage will be positive going like this. So it will just keep changing like this. That's what you can see here. I'll just go back to this and try to show you. See now, when the input is positive, so let me show you my graph and this. So when the input is positive, what you are getting? So this is, see now, okay, let me just stop this. So is this my input voltage positive here, red one? So when the input is positive, which is over here, so what the output is minus. So this would have been minus 1000 volts, but you cannot go beyond the supply voltage, and it is not even the supply voltage. It will be saturating at a voltage which is less than minus Vsat, and it will be saturating here. Of course, when I say less than minus Vsat, means if it is -5, it will be -3, -2.8, something like that. So this will not be even going up to 5 volt. It will be 4.8, 4.3, whatever the amplitude is. So we are trying to understand what is this amplitude. I'll call this as plus Vsat. I'll call this as minus Vsat. So now I have opened the this. I don't have this resistor now. I have opened it, and then you can see this is going up to plus Vsat, minus Vsat. I have to first measure that. How do I measure? Go to this view. You have measurements, and you can add define measurements in channel 2. I want to know what is maximum and minimum. So this is actually plus Vsat and minus Vsat. So you can see these two are not even same also. So this is the practical value that you are having. So let me go back to my tabular column and try to fill in the values that I'm supposed to write here. So as per my observation, the plus Vsat is 4.3 volt. This is 4.32 volt, and minus Vsat is minus 2.85. Minus 2.85. So now we are done with the values of getting the values of plus Vsat, minus Vsat. We could able to find out. So it is now. So the plus Vsat is 4.32 volt and minus Vsat is minus 2.85 volts. This will be different for different op amps, and you can see this need not be exactly opposite of that. That means the amplitude wise, magnitude wise, it need not be same. Whatever it comes, we have to write. Okay, now so once we have this as the thing, so if you can see this is minus 2.8, that is plus. Okay, 4.3. So suppose if I write it to the scale, can you see this comes somewhere here, and this is somewhere there. So if at all if I want to get a proper waveform, so I'll be getting the negative peak only this much, and the positive peak should also be the same here. Suppose if you try to go beyond this one, what happens? It just clips here, whereas it is coming fine. So what is the maximum swing that you can expect? The maximum swing that is possible here is only this much. That is, from here, whatever I get, I can get the same value over here. So this is what we are writing. So V naught maximum, the output maximum swing possible is minimum of this and this. So what is the minimum of, okay, 4.32 and 2.85? So in this case, the maximum output swing you can have would be minimum of 4.32 and magnitude of minus 2.85, which is nothing but 2.85. So 2.85 is the maximum swing that is possible in this op-amp circuit. That is peak. So what is V naught peak to peak possible? It is 2.85 volt into 2. So this is the maximum output swing that you can think of without any distortions in the. So this is the amount of swing that you can expect. So now after knowing this, so this is important. We will try to find out, okay, why it is so important to know this. Okay, output peak to peak maximum available swing. So what we'll do now is, so let us try to connect the value of RF and try to get the amplification. So now I'll get back to this circuit and I'll connect the value of RF. So let me keep changing the value of RF and try to understand what is the gain of the amplifier. So now, so as we know, this is the expression for AV, which is minus RF by R1. So I'm keeping the value of R1 constant, which is 1K. So this is kept constant, whereas this is made as a decayed resistance box, a variable resistance. So now I'm actually writing for different values of RF, which is 100 ohm, 800 ohm, 1K, 10K, 22K, 100K, what is the corresponding value of AV, which is just this divided by 1K, this divided by 1K, this divided by 1K, everything is divided by 1K, so that you have this as the gain. So now we can see now, so we know what is input maximum. Can you see this is? Using this expression, I need to find out what is the maximum input that I can apply so that I'll get the output voltage without any distortion, So this I'll again calculate using the equation, that is using this. So what is V naught max possible? It is 2.85 divided by of course AV is just take the magnitude. It is, in case this is 0.1. So you can apply 28.5 volts as the input you can able to apply. So you can apply up to 28.5 volts. So for this one, so you had, okay, let me just do this 2.85 divided by alpha A. So calculate. So A is 0.8. So how much you can apply? You can able to apply 3.56 volts. Then you can able to apply 2.85 volts. How much you can able to apply? You can able to apply 0.285 volts. How much you can able to apply here? It's again 2.85 divided by 22. So you can able to apply 0.129, that is you can able to apply 129 millivolt. Then you have 2.85 divided by 100, so you can able to apply 28.5 millivolts. So what are these values is, if I keep the value of RF as 100K, I can apply only 28.5 millivolt as the input, so that I'll get a proper output voltage, which is not like clipping. So this will not be clipping. So now if it is 22, I can even apply up to 129 millivolt. If it is 10 kilo ohm as your RF, you can able to apply 285 millivolts. So this is, we know the range of input voltage that I can keep so that I can get a undistorted waveform. So let us try to identify what is a practical input voltage that we can able to keep. So because in my AD kit, if we just go to AD kit and try to find out what are the maximum input you can apply is hardly 5 volt. You can see you cannot apply anything more than 5. See, this is the maximum. So let me write this as only 5 volt. So this is now only 5 here. Let me apply only, so let me just write it in a different color. So this is 5 volt I'm applying. Here I'm applying 3 volt. Here I'm applying, let me assume that, let me apply only 2 volt. Let me apply 0.2 volt. Let me apply 0.1 volt here. Let me apply some 20 millivolt. These are the input voltages that I'm practically applying. So let me just write this as a circled one, if for all practical measurements. So this is practical applying. Now this is practically applied signal. So let us, okay, let me just write this as a star if it is a measured one. So this is measured one, this is measured one. This I'm going to calculate. Okay, now for star I'm going to measure it. So what I'll do, I'll keep the value of RF as 100 ohm. So this is 100. I'll keep all others as so now I'll go back to this. So how much I can able to apply? I can able to even apply 5 millivolt, sorry 5 volt I'm applying. So I'll go back to this and I'll run. So what I'll do now is, so this has came up. Okay, let me just connect it now. Okay, this is fine. So what I've done now is I have applied RF. Of course I made the value of this as 100 ohm and R1 is 1k. Now we are expecting a gain of 0.1 and of course minus 0.1, the output will be out of phase. I'm applying 5 volt amplitude. So let me just go back here and try to measure the input output. So what I'll do, I'll make this okay 100 millivolt. Okay, this distortion is due to my AD kit, so don't worry about that. Let me make this 2 volt per division. Let me make this also, if I make it 500. Okay, you can see now I have to measure the peak to peak. So let me measure the peak to peak of my input and output. So this is output peak to peak and input peak to peak. So this maximum minimum is no more required. Let me remove this, otherwise it will be confusing me. I will remove this also. I remove this. Now let me stop. Okay, don't worry about this distortion. So this is due to my AD kit issues. Okay, fine. So let me bring it back. So if you can see the input signal, which is 10 millivolt peak to peak. So that's what I'm writing here. See now, what I'll do now is I will take a screenshot. So maybe I'll stop and take a screenshot and put it in my one of my Word file. So what I'll do is I'll create a Word file of my Opamp circuit. So just a minute, I'll close this. I'm unable to edit now. Now I can see. Now this is my first waveform. So if you can see, the input amplitude is 10.06. Okay, let me write it as this is 10.02. Output is 1.03. See, these two are the readings. So this is the reading what I have. The input peak to peak is 10.02. Output peak to peak is 1.03. So if you can actually find the gain, it is now 1.03 divided by 10.02. The gain is okay. It should be okay. Let me divide that. Okay, just So this is divided by, you can see the gain is 0.102. So this is just the magnitude of the gain. So this is magnitude of the gain because the output is out of phase. You can see the output and inputs are out of phase. This is reducing, that is increasing. So now I have the gain as, okay, minus 0.1 to be exactly. Okay, this I will not be measuring for gains greater than or less than or equal to 1. So less than or equal to 1, I will not measure this. So I will not measure this. I will not measure this. So from here onwards, let me measure the gains, RA, the frequency response. So now let me increase the value of RF from 100 ohm to 800 ohm. So I'm just increasing now. So this is 200, 300, 400, 500, 600, 700, 800. So this is now 10, 9, 8. Okay, I have increased it to. So let us go back to our, see now, the moment when you make this RF as 800 ohm, I have to keep an input voltage which is, if it is 5 volt, you're in trouble. So let us see what happens if I'm there in 5 volt, what is the trouble? I should adjust this to 3 volt. So now what I made is, I simply made RF as 800 ohm. I didn't change the amplitude is still 5. Let me see what happens. Now. So let me make this also as 2 volt per division so that you can see. If I run, you can see this is what I'm getting. See now, this is clipping here, this is clipping here also. So why it is clipping here is the output cannot exceed plus Vsat and output cannot go below minus Vsat. So that's the reason why it is being clipped off. So that you can verify over here. So since the maximum input that you can apply is 3.56, but you applied 5 volts, so that's why it is clipping there. So what I have to do now is I have to apply the input amplitude of hardly 3 volts. You'll get it properly. So what I'll do, I'll go back here, I'll make this equal to 3. I'll make this equal to, maybe what I'll do is I'll just put this aside. Okay, I'll just split this into 2 halves. So let me take out this scope out. You can see now it is actually clipped off now. So maybe you can just make it half. So now let me keep it, this is actually running. So I'll make it equal to 3 volt. The moment I make it equal to 3 volt, you can see we'll get a proper waveform. Can you see? Are you not getting a proper waveform now? So waveforms are fine now. So let me make it, both are in 2 volt per division. Now you measure what is peak to peak. Now we have applied the input voltage as per our calculation, which is less than 3.56. Even you can able to apply 1 volt, 2 volt, 3.2 volt also I can apply, but it should be less than V in max that you can able to apply. So we have applied 3 volt. Let us find what is the input voltage and output voltage peak to peak measured values. So let me just go back here, and then if I can see, let me stop this. So can you see what is C1 peak to peak is input. C1 peak to peak is input, which is 6.03. C2 peak to peak is output, which is 4.91. So let me take the ratio of 4.91 divided by 6.03, which happens to be 0.814. So this is my, okay, let me take a screenshot of this and put it over here. So first one is for a gain of minus 0.1, second one is for a gain of minus 0.8. See now, this is what the gain I have. So this is the magnitude of the gain, input peak to peak, output peak to peak, and this is my gain, which is a calculated one. So star is measured. So let me write, star is a measured value. So this is the input that is kept. So now, so I will do this as double star. So what is this double star? Double star is calculated. So it is just a ratio of this by this. So now I will change this to 1K. I'll change my RF to 1K. So what I'll do, I'll make this RF as 1K. Go back to this. So I have to keep my input voltage as 2.85 or should be less than 2.85. We just kept it as, we'll keep it as 2 volt. Let us try with only the earlier voltage as 3. Let us see what happens. As I changed it to gain of 1, can you see it's already clipping here? It's already clipping because at the bottom I have a limitation. At the top it can go up to 4.3 volt, but here it has got a limitation of minus 2.8. That's why it is clipping first here. That's why it is clipping first here. So how do I avoid this? So why this is clipping is because you have applied an amplitude which is more than the calculated one. So we actually calculated the input as maximum 2.8. When I apply 3 volt, I'm in trouble. So let me apply hardly 2 volts safely. So what I'll do, the moment I apply hardly 2 volt, you can see what happens. So let me just change this, make this screen bit smaller so that you can see simultaneously. When I make it 2, see, are you getting it properly? So this is perfect. So the output input waveforms are first have to be in good shape, that is both should be sine wave. Now measure the input peak to peak and output peak to peak. So C1 peak to peak is 4.0. C1 peak to peak is 4.03. Output peak to peak is 4.08. So now it is 4.08 divided by 4.03. The gain is 1.012. So this is the expression. These are the values of input peak to peak, output peak to peak when the gain is 1, when the gain is minus 1. The value of RF is 1K, R1 is also 1K, so gain is minus 1. So let us go to next value where you have the value of RF as 10K. So that will result in a gain of minus 10. I have to apply 0.2. So let me make this, the moment I make it 10K, you can see it is clipping. So I'll make that 10K, I'll make this 1K as 0. Now I have to reduce the input amplitude to, what should be my input amplitude? My input amplitude should be 0.2. Let me go back to this and adjust this amplitude to 0.2. See now when I'm having this, your output is perfect. See now, let me stop this. Maybe you can make this dimension bit, okay, this bit smaller. See now we can measure what is input peak to peak, output peak to peak. The measured values of input peak to peak, output peak to peak are, let me stop it here. So what is input peak to peak? It is 426 millivolt and output is 4.107 volt. So what is this now? It is 4.107 divided by 426 exponential minus 3. The gain is 9.64. See now, so let me just go back here and try to find out. See, this is input peak to peak, output peak to peak, and this is my actual gain. This is the intended gain. So why this is that negative is not seen? Because it's out of phase. The negative will going to come since we are finding the magnitude, it is on. So negative is hidden in this opposite out of phase signal. So now we will do the frequency response. So what I'll do is, so we will do the frequency response also. For that, let me add network. Okay, I have to have a frequency starting from very low frequency of 50 Hertz. You can go up to around 500 kilohertz. Okay, now step can be okay, fine. This is C1 fine. And then, okay, you keep the amplitude as 200 millivolt only. And we are expecting a gain of around 20 dBs, so that you keep it around 40 as the top. Bottom, you can keep it around, even if you keep it around minus 40, it is fine. Now, if I run, what I'll get? I will get a gain of 20 log of 10, which will be 20 dB. And you can see this is how the plot is coming. So you can see this phase is 180 degree, which is the indication of that negative sign. So this is 180 degree. So what I'll do now, I will stop and I will place cursors. So I will place cursors. So one normal, one delta. I'll keep the normal one in the DC gain, that is at low frequency. The other one I'll keep such that this is minus 3 dB. So I'm just keeping there so that it is minus 3. Am I there? Okay, I'm almost there. So this is, so now this is my, so as per this, the gain in dB is again 20.12 dBs. Bandwidth is, this is my bandwidth. So this is my bandwidth, which is corresponding to 3 dB bandwidth, which is 37.35 kilohertz. 37.35. So let me write it as kilohertz. This is the gain. This is the gain, which is the DC gain, and this is my cutoff frequency. This is my bandwidth, cutoff frequency, bandwidth, and of course we don't have cutoff frequency over here. So I'll take one screenshot of this and keep it in my. Okay, let me also have the corresponding what. So I will have my time response also here. So this screenshot also I'll take and I'll keep it over here. So this is the frequency, sorry, time response for a gain of minus 10. This is the frequency response. Of course, we need to fill in one more value here. So I need to fill in this volt, AV, volt per volt, which is nothing but how we actually find this is actually 10 to the power of 20.12 divided by 20. So this is gain in volt per volt, 10 to the power of 20.12 divided by 20, which happens to be 10.13. So this is 10.13 is the gain of the amplifier magnitude. Again, magnitude of the gain in frequency response. You can see all of them are same. So don't worry that this is 9.64, this is 10.13. This is fine. Okay. Now the gain bandwidth product is this into this. So it is now 10.13 multiplied by 37.35 kilohertz, which will be 378.3 kilohertz. This is again kilohertz. So this is for a gain of minus 10. So let me make the gain as minus 22. How do I make it 22? So I will change the, okay, before I make it 20, okay, let me make it 20. Now it's actually in 10K. This is 20. I'll increase 1K by 2. 1, 2. So I actually have now 22K as my RF value. So what is the corresponding value of input? The input should be 0.1. Input should be 0.1. So with this 0.2, you can see it will be get clipped off. So let me go back here and try to see if that is clipped off or not. Yes, it is clipped off. If I run it, you can see it is. What happened? Let me just go back and try to see what has happened. So this is my signal. Okay, I had to turn on because when I'm running network, my wavegen will be off. I need to turn on my wavegen. So don't panic. So you can see now it is clipped off because my wavegen amplitude is too much. So I have to reduce my wavegen amplitude to 0.1. You can see since it is 0.2, it is clipping off both at the top and the bottom. If I make it 0.1, it would be fine. See now, the moment I make it 0.1, everything is perfect. So now I made it 0.1. Let me make this like this. Let me stop it. See what is input output peak to peaks. The input peak to peak is 214.6, okay, 64 or 69 millivolt, and output peak to peak is 4.46. So what is the gain now? it is 4.46 divided by 214.64 exponential minus 3 millivolt, that is 20.77. So the gain is now 20.77. So this is what, okay, let me take one screenshot and put it here as my next reading. This is for a gain of 22. It's for a gain of minus 22. So I have these as my readings. See, now this is my what the input voltage 214.64 millivolt, the output is 4.46, the gain is 20.77 against 22, again the magnitude. Let me go back to network and try to get what is, again for network you have to be careful. So what is actually 20 log of 20, sorry 22, you are expecting 20 log of 22, which is around 26 dBs. Suppose by mistake, if you don't change the amplitude to 100 millivolt, and if you run it, we are expecting a gain of how much? 26 dB. You can see you're actually getting 24 dB. So don't be satisfied with this 24 dB, because hardly 2 dB difference. So why it is happening so is because your input amplitude is more than what is permittable. So why do we say it is permittable? This is what we found out here. So input amplitude has to be 0.1. You cannot keep more than 0.1. Actually you kept 0.2. So what I have to do? I have to make it 0.1. Then you'll get proper waveform. So how much you're expecting? You are actually expected 26 dB. Are you not getting 26 dB? Yes, you are getting 26 dB. So now you stop and then adjust this to 6 dB. Sorry, 3 dB. This is minus 3 dB. I hope you got this point. So don't get compromised with slight values different. Make sure that you are making the proper adjustment. Then if at all if it still differs, then it's fine. But don't make an error of as we did there. So instead of keeping 100 millivolt, if you give 200 millivolt, it's the circuit error. So now it's minus. Now let us write the values. It is 26.93 dBs and bandwidth is 17.71 kilohertz. And what is this in dBs? It is 10 to the power of 26.93 divided by 20 is 22.22. This is 22.20. So what I'm trying to do here is we found the gain in dBs is 26.93. So and its bandwidth is 17.71 kilohertz. So this is gain in volt per volt. How I did this? 10 to the power of 26.93 divided by 20, which comes out to be 22. So let us find out what is the gain bandwidth product. This multiplied by 17.17, which is 381. You can see this is 381. Can you see the gain bandwidth product is almost constant, meaning as the gain increases, bandwidth reduces. So gain has increased from 9.64 to 20.77, whereas bandwidth has reduced from 37 kilohertz to 17 kilohertz. So this is what we were trying to understand in other amplifier circuits also. If the gain increases, naturally the bandwidth will certainly reduce. Now let us go to the last one, where we are keeping the value of RF as 100k. Made the 100k 1. This is made 0. That is also made 0. I have to keep amplitude which is 20 millivolt. Now actually we have kept now 100 millivolt. For this value you can see it will be get clipped off. Suppose if I turn on this and see the scope, you can see it's a clipped one. I'll run it. You can see it is clipped off. Why it is clipped off? Because your input voltage is too much. So what I have to do now? I had to adjust my input amplitude to how much is calculated as per calculation. I have to keep, even you can keep 20 millivolt. So I'll go back and keep it as 20 millivolt. The moment I keep it at 20 millivolt, I'll get it properly. See now, are you not getting it properly? Yes, you are getting it properly. Maybe slightly adjust this to 50 millivolt, and you can make this, okay, it is a bit distorted. Okay, let me just make this so now let me stop this. What is input peak to peak? Okay, input peak to peak is very bad because it is now taking all these spikes. Let us not measure from this. This is an erroneous measurement, because what is actually input applied is, if I run it now, if I run it, it is, how much is input that I have applied is hardly 20 millivolt. As I'm supposed to get 40 millivolt peak to peak, how much you're getting? So this is 74 millivolt, which is not correct. This is because of all these errors. So let me take, of course, this is what some adjustment you have to make. I cannot take it as 74. If you actually take 74 millivolt and then 74 milliwatt, and then if you take the output as 4.13, so how much gain you're going to get? Gain will be so less. It is 4.13 divided by 74 exponential minus 3. The gain happens to be 55. Gain happens to be 55, which is not correct. So let us take the input amplitude as around as twice the input that we have kept here. That is input that we have kept is 20. That is peak. The peak to peak is actually 40. If I take this as 40 millivolt, this is actually the input applied. This is because of some error. Error means, okay, spikes are there. So what is now 4.13? 4.13 divided by 40 millivolt exponential minus 3 is, you can see you have a gain of 103, which is very close to your expected value. Correct? So this is what some errors that will happen while taking the reading. Don't simply take it as 74, because here you can see this is 200 millivolt expected, 214 coming, it is okay. The 400 millivolt is expected, you're getting 426, it is fine. You expected 4 volt, you're getting 4.03, expected 6 volts. This is actually peak to peak is twice of that. So in the previous all 5 cases, you got the input voltage almost close as expected, but in the last case you expected 40 millivolt, but you're getting 74. In such case, you cannot simply take it as whatever that you're getting. So you have to make a proper decision, take it as 40 millivolt, and let us run this network and try to see. So what I'll do now, I will run the network. This is my network. I will run it, and I'll make sure that the input amplitude should be 20. So how much is the expected gain? So 20 log of 100 is actually 40 dB. Let me just make this slightly more. Are you now getting almost close to 40 dB? Can you see you're having almost 40 dB? Stop it here and make this so that it's at 3 dB down. Is this now 3 dB down? Yes, you are almost there at 3 dB down. Okay, now let us find what is gain bandwidth product. So it is 40.12 dB. The bandwidth is 2.36 kilohertz, and what is 10 to the power of 40.12 divided by 20 is actually 101. So 101 into 2.36 is actually 239. Okay, this is what we are getting here. Okay, this is the gain in gain in dBs. This is gain in volt per volt by doing this 10 to the power of 40.12 by 20, and this is my bandwidth, and this is the gain bandwidth product, which is 239. We actually expected very close to this. Of course, ideally speaking, this should be very close to that. So this is the practical value what you have. Don't try to manipulate this. Don't make it 339. So whatever value that comes, you just write it, so that we have to accept the thing what is that we are getting. So let us try to see, is it almost okay? 3 dB. Okay, this is 3 dB. Can I just slightly increase it? Okay, this is fine. So let us not too much worry about if there is some deviation in the expected value. So let it deviate, but we are just following the procedure, and then as per the procedure we're getting. So as the gain is increased from 22 or 22 to 103, almost 5 times increase in the gain, the bandwidth is also reduced by 5 times. So of course it has reduced more than 5 times, it is fine. So this is how you can able to understand the working of the inverting amplifier. Let me just complete this screenshots now. So let me take one screenshot corresponding to this, which is my time response over here. Have I already taken? I don't know. Okay, I think I didn't take the network part of the previous gain. Okay, for 22. Okay, that you can do. Let me just complete this. Let me take the network of this, and let me then again go back and try to get print screen of this. I will take the network of this, and I had to take the network of 22 kilohertz. Sorry, 22 as the gain. So what I'll do is I'll make this 22 and then make it as 100 millivolt, and then okay, 100 or whatever, even if it is 50, there's no issue. So I can even keep lesser than 100, you can still get same 20.770. How much is the expected value? So this is what is 26 dBs you expected. Let me stop it. Let me keep this at 3 dB down. So this is there at 3 dB down. Okay, this we have it as 17.71 earlier. Now it's almost very close to that, 18 kilohertz. So let me take a screenshot of this, place it here. Put it at this. Okay, these are all the time response, frequency response. So time response, frequency response of each and every. So let me put this next to this. So time response, frequency response, time response, frequency response. These are all just the initial time responses for gain less than or equal to 1. That's it. Okay, that's how you can able to do the experiment. Thank you.